All right, welcome to episode 10 of Bit by Bit. In this episode, we're going to talk about addressing modes. We're going to follow chapter 7 of the Wagner Torrance book. And let's just get started. So, one of the things that this is going to be talking about is memory and how to access it. And so, before we kind of decide on how to access, we probably ought to decide where it is in memory. And so, there's quite a bit written on this. It was very confusing to me to try to parse it out in 2025, having never used a real Apple other than maybe once or twice here and there. And so, one of the things that I noticed right off the get go was that there were probably 50 different memory maps for the Apple. And I thought to myself, as I generally do, wow, that's crazy. And so I thought, surely there's like some just general guideline on what to use. And really, there isn't, but let's see if we can make sense of it together. So I pulled up from the what do they call it? Comp.this.apple2 programming FAQ. Some important kind of pieces of discussion around this stuff. And so this section 15 of the fact says, what parts of Apple II memory should a user be careful about modifying? Because I figured, well, that's probably good to stay out of those. And it gave us a list of addresses where things are kind of important. And I thought, well, that's interesting. And then I read on and it said something about zero page addresses. And out of zero page, which is the addresses from 0000 to 00FF. Okay, so 256 addresses. And these are all those addresses. And you can see that they're just completely used by all kinds of stuff. We got AppleSoft with the A, M with the monitor, 3 with DOS 3, and then so on and so forth. But generally, we're booting off of a DOS disk or something. So anything with an A, an M, or 3 kind of used. And then we remember that in chapter 5, the author talked about, well, the addresses 6 through 9 were okay to use. And sure enough, they're empty. There's another set up here at EB through EF and FA through FD that are also unused. But generally in the zero page, we're just going to pretend like it's all packed with stuff and used by everything. And if we want to use anything out of the zero page, we'll use 6 through 9 like the author recommends. And then I found this Relay guys, John Relay's Apple II map for all apples. And it looked a little bit more useful. All right. And to help us understand it, it looks like this. This zero page is that 00 to 0FF. And we know that there's like 6, 7, 8, and 9 are the only four addresses we can really use there. And then there's the stack. We don't want to mess with that. There's the input buffer. We don't want to mess with that. And that's going to fly in the face of the very first example the author gives in this chapter, where he puts stuff at 204. And it is dependent on the input. So we're going to skip on that. We're going to pick a different set of addresses. But we notice that 300 is pretty free, 300 to 3CF. And then it gets taken up by DOS and stuff. And then there's these video pages. And then there's this other free space area here in the C00 to 1FFF range. And then there's high-res graphics pages and AppleSoft string data. So those are all, it's not right to say that they're all used because they're not. They're only used if you're doing that sort of thing. So the zero page is pretty full. We saw that. The processor stack will be in use when we use the stack, when we make function calls and stuff like that. And that'll be when it's used. But we generally don't mess with that because it could be used. And then the input buffer, we don't really want to mess with that because that means like when we're running, I'm thinking it's AppleSoft, but regardless, AppleSoft or DOS, something's using it for their input buffer. So when you're pressing keys and stuff, it's changing the values in those locations. So if we wanted it to be predictable, that probably wouldn't be great. The free space stuff here from 300 to 3CF is free for us most of the time. And it's free even when we're in Merlin. So we'll try to put our stuff there. And that's like 244 addresses or so, which is more bytes than I'm going to type in, manually. So it's probably good enough for ours. But if we need more, we'll put it up here in the C00. But let's look at these others. So this DOS, ProDOS, and interrupts, if you're running one of those And when we boot the machine, we're not. But when we boot it to a floppy that has DOS on it or Merlin or something else, it's going to have these running. So we don't want to mess with those addresses. The text video page and peripherals and the text page 2, these really are the peripheral thing has me a little bit concerned that that might be running, but we're not really doing text video when we're running our programs. And so as long as when we run our programs, the addresses are not in conflict with those that might be doing something else, we can clobber them. It's not going to hurt anything other than if we had text video up and we wrote over that, then it would mess with that. And then the free space thing's good. And the same thing goes for the high-res graphics. If we're not doing high-res graphics, we can write into these memory locations all day long. Okay, but then if we try to run graphics in our code, we get some really wonky results. Same thing here with AppleSoft string data. If we're not running basic and we don't have a lot of strings, this is pretty free. Okay, so it depends on what's running when. And so when we write machine code, we're usually running inside of the monitor, and the monitor is usually running in DOS, or like I'm running it right now, it's just by itself, but it's still got AppleSoft is still there, it's still resident, and the monitor at a minimum. That's when we boot off the ROM. But if we boot a disk for DOS, then it's got DOS, the monitor, and AppleSoft. We don't want to clobber any of their addresses unless we don't care. Like if we were writing a game and we wanted to take over the machine, we could use any addresses we wanted to pretty much, as long as we didn't clobber any kind of routine we want. Like if we wanted to use a DOS input output or routine or something, well, we wouldn't want to clobber it. So I hope that makes sense to you. Doesn't really, it was hard fought knowledge, let's just say. And what I took away from it at the end of the day was try to keep my simple experiments in the 303 CF range. But if I'm going to write a more extensive program, I can consider putting it up here in 800 or C00 and up, that type of thing, because this is quite a bit more space. And if you're using Merlin, it talks about using 800 to like 800 to FFF, which is still quite a bit of room. So until we get into something more extensive, like writing an entire game out of assembly, all that's going to be good. And we'll be able to enter the monitor, exit the monitor, enter basic, exit basic, enter Merlin, exit Merlin without clobbering stuff that we'd have to be more careful with if not. So that's a bit about that. Now, onward to the book. So the book talks about some addressing modes of how to access that memory that we're using, mostly in the 300 range for our examples. And then it gives us some examples of basic modes. And these are very typical of microprocessors or microprocessors, like the 6502 or the 8080 or any of those. They have very similar sets of addressing modes. And to the degree that the addressing modes are very rich, is kind of the programmer experience is pretty nice. If it's very limited, then the programmer's got to jump through hoops to get things they want. Another thing to be aware of, and I talked about this in an earlier video, though I didn't really know what I was talking about then, and I still may not, but I know a little more, is that orthogonality of the instruction set. So if to the degree, this is speaking to the degree to which each of the addressing modes applies to various instructions. So if you're able to use basically all of the addressing modes for all the instructions, you have a very orthogonal instruction set with respect to the addressing modes. But if you have some instructions only have one type of access and others have many, then you don't have the orthogonality, which the only problem with that is the overhead, the cognitive overload of like which ones are which. But like, for example, this instruction he talks about here, transfer from the A register to the Y register. Why would I need all these other modes when the only real mode that matters is moving it from the accumulator into the Y register? And so, orthogonality is great. It doesn't, it's not a religion. Moving on. So let's just sort of take a look at these. I'm going to switch to another page in this text, the reference page, because it has these repeated. Now, you'll notice that this has immediate, absolute, zero page, implicit, relative indexed, and then indirect indexed and stuff. When we get to the reference page, they don't use the same exact language, but they do use the same exact syntax. So we'll note that when we get there. But without further ado, let's scroll down and get to the reference page. Okay, LDA is the one we're looking for. It's this one here. I'm going to zoom in so we can see it a little better. There we go. And we can take care of it. So with that in mind, let's remind ourselves how this is written. So we have the instruction, the mnemonic, which is LDA, load the accumulator. We have the operation is specified in shorthand. This says move whatever's in memory to the accumulator. There's a description underneath the mnemonic. It says load memory into accumulator. Those are the same thing. And then we have our different addressing modes for this instruction. Then we have some syntactical examples, machine code, and then the number of bytes that are taken, as well as a time in microseconds of the instruction. And then which flags are messed with. With load the accumulator, there's two flags that are affected, the negative flag and the zero flag. So that's what this represents. We're going to jump into the hands-on here in a minute, but basically for this immediate instruction, we're gonna note that the assembly language for that, the syntax would be LDA $FF. That moves FF into the accumulator. The way it's gonna sort out when we look at it from machine code perspective is there will be 2 bytes involved. The A9 byte, which is the opcode that says this is an immediate load the accumulator. And then the second byte is going to be whatever we want to load it with, the FF. So A9FF is going to be for this one. If we were doing 0 page, it would be A5 and then F. In this case, it'd be FF. But they're slightly different. We'll get through them. So let's just go ahead and start the simulator. So I've already started, but I'll restart. This is Virtual 2 because I'm on the Mac today. It works the same way as Apple Win does on Linux or on Windows. And for booting and all that kind of stuff, I'm going to use these buttons. And I've also set it so that when you hit the Command key, because I'm on a Mac, it acts as Open Apple, which is useful when we get into Merlin for hitting Open Apple Q and stuff like that. I have a caps lock turned on so that when I type in here, it'll be capitals. And without much more, let's just get started. So I reset it. We're in AppleSoft Basic in ROM. I'm going to call into the monitor, call 151, and we're in the monitor. So if I look at the 300 memory location, which is on page 3 of the memory, if this was 0000, this would be page 0, but this is really page 3 of, you could think of it as a 256 page book, okay? But basically this is the first byte on page 3, second byte, so on and so forth down the way. And they're all FF, which means they have not been initialized. So we have a clean machine to work on. Let's load the accumulator. So reminder, Control E, Enter gives you the registers. Another way to do it is 45.47, 45.49. Wow, that's crazy talk. 45 dot, and then 45, 46, 47, 48, 49. That shows all the same bytes, okay? As if we typed Control E, Enter. And we can make mods this way as well. So right now, the A register has FF, X has FF, Y has FF, and so on. Basically a nicely, cleanly booted machine with nothing really going on yet. But what we want to do is we want to load the accumulator with a value. And we'll use this FF value, except we have FF there already. How would we know it worked? Well, one way to do it is to set it to something else. So I said 45:00. Now if we look at it, it's got 0 in the A register. All right, so we can do the A9, we can do the load the accumulator with FF. And the way to do that is we can just type it in at location 300. We can type those machine codes. So the A9 and the FF. So A9, FF, and then 00 will give us a nice break. And if we look at this in machine code disassembled, it looks like this. We have the A9, FF, and 00, which is load the accumulator with the immediate value, FF, as specified, and then it'll break. We can run this right now, but before we do that, let's check the registers one more time. Registers are 0. The accumulator has 0. And we want to put the immediate value, whatever we specified in the next byte, which is hex FF. We want that to go in the accumulator. So let's run it and see what happens. Boom. All right, it runs, it breaks at the next instruction after the break, which 300 was A9, 301 was, what was it, FF, and then 300, 301, 302 was the break instruction. And then it moves the program counter up to 304 and stops. So what is in the accumulator now is the FF. So that worked. And we can try it again. Let's see what our code says. And what we'll do is we'll just change 301. We look at it, it's FF, right? 301, and actually put it there. 33. 300L. Okay, A933. So now it's going to put 33 into the accumulator. And right now it's still FF. So we do 300G. It runs again, it stops in the accumulator as 33. So we see right away that we can experiment with this directly and see that this instruction does exactly what it says it's going to do. And if we wanted to, we could even explore a little bit on the negative zero flags, but I'm not going to do that right now. But if you supplied it with a negative number, then the processor status flags would reflect that. All right, but let's move on to the zero page. Now, zero page is page 0. That's the whole point. And then this number that you supply here is an offset into the zero page. So supposing that the zero page memory location 6, which we said was available to us, that we set it to something known. So we're going to set it to 6 colon, I'm going to set it to 22. All right, and then we look at it, and sure enough, it's 22. So that's where it is on the zero page. So we're going to load the zero page, load the accumulator from the zero page. So what we were looking to do is something along the lines of LDA $6, and that would load 22 into the accumulator. But we got to do it with machine code. So instead of LDA $6, we're going to go A506, and that should work. So we're going to go 300, A5, then 06, and then a break. We're going to list it, make sure it translated right, and it looks like it did. A506 is LDA 06, and then it's going to break. Right now, the accumulator has a 33 in it. Afterward, it's going to get whatever's in 6, which is 22. Let's run it and confirm. Yep, it worked. Okay, we changed the value in 6 to something else. Let's go with 34. See that it changed. Yes. Run the thing again. Yep, that's some crazy stuff. 300G. And we get 34 into the register. So it reads it direct off page 0 at the location we specify after the instruction. There's another instruction that takes an offset, and it'll let you do some math on it. You can start at a base location in the 0 page and then supply an offset to it. So let's try that. So the assembly is LDA $FF, comma X, okay, where X comes out of the register. So we have to set the X register. Right now it's FF. And we said that this was 45, 46, 47, 48, 49 in memory. So we can see that X is FF by going 46. And we see it's FF, and we can set it. So let's set it to 6. Okay, and then we'll look at the registers and see. There it is, X is 6. So now if I do LDA FF, or LDA $00, comma X, it'll add 6 to 0 and get 6, which is what we want. So let's try it out. Let's see, 300 colon, and then instead of A5, it's B5. That'll tell it to use the X register. B5, and then we have to give it a starting location. All right, oops, I like that. We're just going to give it a starting location of 0. That's the location on the 0 page that we want to start with. And then we're going to add the X register. And then we can bump X and get it to move it along. And we'll do 00 for break here. Let's look at that, kind of explain it a little. So B500 is the 2-byte instructions that go for the 0 page X reference. And it starts with the offset into the 0 page of 0. And then it adds whatever's in the X register, which we said was 6. So it's going to really, effectively, it's going to go out and get whatever's in 6 and put it into the accumulator, and then break. And let's see what 6 looks like. There it is. It's going to put 34, and we already have a 34 in there, but we can change that to 0, 0, and then take a look at it. Okay. So if we run it now, it should get the 34 back. And it does. All right. So those are those addressing modes. They're those simple ones. And then we get into something called absolute. And the difference between absolute and zero page is it's not the zero page necessarily. We could do, and we probably will, do an example where we use an absolute address for a zero page reference. So we know already that we have, in 6 we have 34. Let's put something in 7. And just to be kind of, whoa, I don't know what I pressed. 7 colon, and let's put 35 in there. Okay, and then 6 to 9, just to see what's in there, 34, 35 FF. So we have in 7, the absolute address is 0007, and the page 0 address is 707. Let's modify our code to work with absolute addressing. So the absolute addressing mode for pure absolute is AD. So we'll do AD. And then we have to specify in 2 bytes. See how it takes 3 bytes? The address that we want. And we want 07 because that's where our 35 is. And we do it in reverse order. The low order bytes first, and then the high order bytes second. So that's the page numbers after the offset. So this is the 7th address in page 0. And then a break. That's the theory. Let's see what the result is. All right, it says load the accumulator with absolute value of absolute location of 0007. That's correct, and then breaks. And so right now, the accumulator has 34 in it. After we run our code, it better have 35, or we've done something wrong. We run it, and sure enough, we get 35. All right. Let's put something in 8. Let's say 36. And then let's look at 6 to 9 and see what's in there. Yep, 34, 35, 36, sure. So we're going to use 06 as a base address, and we're going to add 2 to get that 8 address. But we're going to do it with this absolute X type of reference. So we got to put something in X. We're going to put 2 there. 1, 2, actually we'll put 3 there. Okay, which is this A register is 45. It's in the 0 page 45. And then 0 page 46 has got the X address, which we can see here. Type 46 and we get 6. So we're going to set 46 to 3. Then we'll check our registers. And we see that X is now 3. So if we did absolute and we set it to 6, and then we added 3, that would be 9, which will get us an FF. Let's see. We want to set X to 2. Wow. Okay. We'll hope. Maybe I'm like smoking something. Let's see. Okay, we want to do this. We want to change our code now. So in 300, we're going to change it to, in this case, we're going to use this absolute X reference. We're going to put X has got our offset, and then our base address goes into the immediate byte after. That's 3 bytes. So BD, then the 2 bytes of the address. And the 2 bytes of the address are, we said 6 was what we were going to do. So the low order byte first, the high order byte second. That's it, and then break. And let's see what happens when we list it. All right, so this is going to load the accumulator from this address as the base address plus this offset, which is 2, which seems like it ought to be 8. And whatever is an 8 should get loaded in the accumulator. We'll check it. Accumulator currently has 35 and 8 has 36. So let's run it and see what happens. The accumulator has 36, so that worked correctly. Now let's do a slightly different version of math. We're still going to use a base address and an offset, but the offset we're going to take from the Y register. So we're going to set Y, 45, 46, 47. So we set location 47 to, let's go 8 from whatever address we're going to say. Really, okay, Y register has 8. Let's change our code. And we're going to use this absolute Y addressing mode. So we're going to do B9. And then we have 2 bytes for the address. And we're going to give it 0000 as the base. And then we're going to let it add 8 to it. That should get our same address of 8. But now let's put something else in 8. Let's see, 98. Okay, and see what's in there. Oops. Yep. Okay, and then check our registers. 36. All right, so with our new version, let's 300L, look at that too. With our new version of it, we're gonna load from address 8 because Y has 8. All right, run it, see that it works. There it is, it has our 98 that it got from address 8. Should be good to go. Now we get into two really sort of sophisticated addressing modes that aren't so simple, although I'll try to explain them in a way that makes sense. And one is called indirect X and one is indirect Y. And he calls this one indexed indirect and this one indirect indexed. And I like that he explains it the way he does and that he does call it that, but this is what we got to get used to. Basically, whatever's in the parentheses is going to get referenced. The math for the address is going to be taken from what's in the parens. So in this case, it's gonna do the index and then it's gonna do the math first, go get that value. This one's gonna do go get a value and then do math and then get that value. All right, so let's look at something real quick. Not real quick, but let's look at it. All right, the first one we're going to look at is called indirect indexed addressing by the author, and I think that's pretty apropos. This is the syntax for it. Load the accumulator with whatever's at this address plus this offset. So it's going to get an address at 80 and 81, the low byte and the high byte of the address. So this is 0200 plus Y. Y's got 4, so address is 204. Goes to 204 and gets whatever's there. We're going to use a slightly different set of addresses because this is the input buffer, and we're going to use something that doesn't get messed with. And then for the second one, we'll use indexed indirect, which is kind of does the math first and then go gets, as opposed to going and getting an address, doing some math on it, and then getting whatever's at that address. So back to my notes. This is what we're going to use is this guy right here. So we know that 6 through 9 are safe to use. We're not going to use those, but we also know that 300 to 3CF is usable, and we are going to use that. So we're going to put our code at 300. We're only going to use a few bytes, and then we'll put some data at 380A for this first example. And this again is indirect index. It means we're going to get the base address, going to calculate an address from that, do some math, and then we're going to get the value from the result. So this is what it looks like in syntax, LDA, $80, in parentheses, followed by a Y. And to simulate it, we're going to put a base address in bytes 80 and 81. We're going to put the low order byte, the 00, into 80, and the high order byte, 03, into 81. And then we're going to put an offset into Y register. So that's going to have 0A. So it's going to get this address from 80, 300, add 0A to it to get 30A, which is where our data lives. And then what that'll look like is this LDA. So without further ado, let's just reset the machine, go into the monitor, caps lock's on, yeah, call 151. And then look in memory and see what's there. 300, there's nothing there. And at 80 and 81, there's nothing there. And there's nothing at 30A either, other than this FF. All right, So we're going to start loading up stuff. We're going to put the base address in 80 and 81. So we're going to say 80 colon low order byte 00, high order byte 03. And that tells it to use page 3, which we're going to populate. We're going to put a value right here at 30A. And let's go ahead and do that. Put the data there. So 30A colon, and we'll put 11 into it. Yes, that makes sense. All right. And then we'll go ahead and code up our program in 300. So what we're going to do is we're going to load the Y register with an immediate value. And that happens to be this byte here, A0. And then the immediate byte, 0A, that's what we want to load into Y. So we're going to type that, 300, 1A0, 0A. It's just funny that it worked out that way. And then B1 is our load the accumulator with indirect indexed. And where it's going to get its base values from 80, and it's going to read the base address value from 80 and 81, which is going to be 0003, and it's going to add that to the Y register, which we're loading here with 0A. So we take a look at it in memory, 300L, and we get load the Y register with 0A. That's an immediate value. There it is. A0 is the load the Y with immediate value. There's the immediate value. Then there's load the accumulator with this, what's in whatever's at address 80 is the address. It's going to dereference that, add Y. It's going to add Y and then dereference. So here it is, 30A. It's got the 11, and we should be ready to go because it's going to load the Y register. We already have 80 and 81 having the address 03. Yeah, it should be good. Let's take a look at what's in the accumulator now, though. FF, it should be 11 when we're done. We're going to run the code, and the accumulator gets 11. And that's called indirect indexed, meaning that we, when we initially do it, we're going to use indirection. We're going to go get whatever's at this location as an address. Then we're going to add, do the math second, and then whatever the result of that math is, which it's 300 plus Y, which is 0A, 30A is the result, then it's going to go get that and put it in the accumulator. So over here in 30A, here's the 11, it gets that, puts it in the accumulator. Very simple and straightforward. I'd take whatever this is, take 4 of this particular part of the video, and then also a lot of background research. Okay, the last mode that we're going to look at is called indexed indirect, and it's got this this syntax where we have load the accumulator with what's in parentheses, and it's an address, $0080 or $80 like this, comma X, and then whatever the X register contains. If it has a 4, it's going to look at location 84 to get its low byte of the address, and then 85 for the high byte of the address. Combine them, get an address, take that, dereference it, pull back whatever data is at that location and stick it in the accumulator. Okay, so what that looks like in my notes is this way. There it is, the same one. And we are going to write code at 300. That'll be our code that does this work. And then we're going to put data at 309. In the last example, we had it at 30A, but we're going to put it at 309. And in order to set this up, we're going to put the base address into 84 and 85. And we're going to use the 300 address, again, because it's safe to do so. So we'll put 0309, which is the address that we want to dereference. So this, what's in here is the math to get this address, the 309, which lives at 84 and 85. So let's boot up and let's call the monitor. Look in the memory and see that there's really nothing there yet. And there's certainly nothing at 84.85. So let's get some values into memory. So we got 84, we're going to set it to 0903, the low order byte first, the high order byte second. So that's address 309, which we can see right here, 309 is uninitialized FF. We're going to put something there. We're going to put 22 there. Let's go ahead and do that now. So 309, we're going to put 22. Now, if we look at the listing again, we see nothing's really changed yet because we haven't coded it yet, but 309 has our 22. All right, and so now let's go ahead and code it up to do the work. So first we're gonna load the X register with 4, which is A204. And if we looked it up in the manual, we would see that A2 is the machine code byte followed by the immediate value. So this is load X register with the immediate value of 4. So that'll load X4 into X. And then after that, we want to use the load the accumulator with the indexed indirect. So what's the index is 80 for the base address. And then it knows about X. And so we're done there. We can do 0, 0 after that. And we can relist it and confirm that what I said was true, which is we got A204, which is LDX with the immediate value of 4. Then we have LDA with 80 plus X. So there's the 80. It's going to add whatever's in X to 80, and it's going to get that. It's going to come back 309. So let's take a look at the registers. The registers are uninitialized at the moment, so we don't really care because we're going to initialize it in code. We're going to put a 4 into X, and then we're going to add that to 80. That'll get 84. We're just curious about what's in 8485, which is 0309, which is our address. So it should work. Let's just run it and see what happens. We got 22 in the register, and we got it from address 309. All right, so that's kind of it. Let's, yeah, we could put something else in 0309. This address here, that we put a different piece of data there and run it again. So let's go ahead and do that. 309 : let's put 44. Let's list it, see that our change took. Sure enough, it did. Let's run it and see what happens. And we have 44 in the accumulator. All right, so hopefully that is clear and made sense after many takes, hopefully. It's not too splotchy and choppy, but it's the best I could do. So after that, in the next video, so I'll try to keep this one contained. In the next one, we're going to write 3 programs. The first one is going to write the word, well, we'll write 3 programs. We might write a couple of different versions of each, or at least of this first one. But what this first one does is it prints Apple to the screen. And it does it in a way that leverages the different addressing modes and some new instructions for Merlin, this hex instruction. And we'll also see that we could also change it with ASCII and just provide the string. And we'll talk a little bit about that. And then after that one, we're going to do this clear screen program, which will just put, if I remember right, blanks all over the screen so it looks like it's clear. And then because it's basically just a grid and you can put whatever character you want in there. So clearing the screen is about putting spaces. It's super fast. You would never know that it was doing it the way it does it. So that's good. We'll try that one. That's going to use some other addressing modes, a variety of addressing modes. And then the final program that we're going to write is one to clear the screen to whatever key press you have. So that'll get us, kind of remind us how the strobing stuff worked in the keyboard. And then also it will have different addressing modes as well. And it'll just be interesting to work through. And so I think those 3 by themselves take up a good video. So see you next time.